So just a quick review of what we were doing. We said that if we have a function f, let's say of x comma y, and then x is a function with respect to, let's say, s and t, and y is a function with respect to s and t, then what is, let's say, the derivative of f with respect to s? So we draw a graph, and this is our f, this is x, this is y, this is st and st. So we draw a graph where f depends on x and y, x depends on s and t, and y depends on s and t. And then when we write the derivative, we say, okay, we want to know how f depends on s. So how small changes in s change f. So first, we need to know, how does f depend on x? So that's the partial of f with respect to x. And then that would be multiplied by the amount that s depends on, that x depends on s. So that's the partial of x with respect to s, plus then how much does f depend on y? That's partial f with respect to y, times how much does y depend on s? That is partial y with respect to s, right? Let's do an example or two. Okay, so let's say we have z is equal to x to the -2 times y to the 6th power minus 4x, and x is equal to u squared times v, and y is equal to v minus 3u. So then the question is, what is the partial of z with respect to u? So let's try to answer this. So this again is going to be partial of z with respect to x times partial of x with respect to u plus partial of z with respect to y times partial of y with respect to u. And so, okay, what is the partial of z with respect to x? So that is going to be this -2 comes down. So you get -2x to the -3, y to the 6th power minus 4. And then the partial of x with respect to u is going to be 2uv, plus the partial of z with respect to y is going to be 6x to the -2, y to the 5th power, times the partial of y with respect to u, which is -3. And then if you want to get the actual answer, I guess you can plug in your x into your x and your y into your y, and that will give you a solution only in terms of u. So that's basically the chain rule. I don't think, are there any questions? Okay. So another important thing that we need to know how to do is implicit differentiation with respect to these type of problems. So let me. So let me do this in the form of an example, and we'll see what happens. But let's say you have a situation like x squared sine of 2y minus 5z minus 1, is equal to 1 plus y cosine of 6zx. So now if you're asked to find, let's say, the partial of z with respect to x, how do you go about doing this, right? So this is an implicit differentiation because this isn't a formula in terms of z is equal to something, but there are z's in the equation. There's a z here, there's a z there, right? So this is implicit differentiation. And you've seen implicit differentiation in Calc 1, but the question is how to do an implicit differentiation in a situation like this. And there are two ways to do this. I think I'm just going to focus on one method. And that's just going to be to rewrite this function in the form of some function. Let's call it big F of x, y, z is equal to 0. So what do we mean by this? Well, it just means take all of this, put it on the other side. So now you get a function f of x, y, z is equal to x squared sine of 2y minus 5z minus 1 minus y cosine of 6zx. And this thing, of course, is equal to 0 because this part is just subtracting this part. And so you get that this entire function is equal to 0. And once we have this function, the formula in this case for calculating the partial derivative with respect to z of z with respect to x is going to be negative of the partial of f with respect to x over the partial of f with respect to z. And similarly, the partial of z with respect to y is going to be negative partial of this f, this function f with respect to y, divided by the partial of f with respect to z. Yes? So what this function is, this is the function that you get when you take this part and you push it over to this side. So you subtract it. So you get this, which is this part, minus this part. And what does that equal? 0, right? If I put this entire thing on the other side, so I basically put a negative here, negative, parentheses, is equal to 0, right? Okay. Any other questions? Yeah.
So is that a standard formula or is that just for this problem?
It is a standard thing to push everything to one side and get 0. And we will see this happen a couple of times. In this example, this is the standard way of, solving this problem. You put it all on one side and then you use these formulas. So now you can solve this implicit differential equation. Any other questions? So let's actually do it. So the partial of f, or let me just do the partial of f with respect to x is going to be 2x sine of 2y minus 5z minus y, okay, and then cosine, so plus sine of 6zx, and then by the chain rule times 6z. Right? Any questions about this? Sorry, what? Okay. And now what is the partial of f with respect to z? So that's going to be x squared cosine of 2y minus 5z times negative 5 plus, or let's say minus y, so plus sine of 6zx times 6x, right? That is the partial of f with respect to z, right? Any questions? Okay, so then in order to finish the problem, the partial of z with respect to x is going to be negative of this part, right? So you just put that down. I'm not going to write the whole thing, but negative, let's call this 1. So negative 1 divided by 2. Yeah, does that make sense? Okay, and that's how to solve an implicit differential equation. Just, again, use these formulas. Again, there is a second way of doing this, but I don't want to complicate it. So you can look that up yourselves. And implicit differentiation, implicit differentiation. Okay. So now let's move on to optimization, which is the next section. Okay, and the first goal is to find minimum and maximum of a function. Let's say z is equal to f of x. Okay, so very similar to Calc 1. Minimums and maximums of functions are very important, especially let's say in physics. The minimum of a Lagrangian is, how certain physical systems behave, and finding the minimum in a regression model will help you create a good data analytics tool. So minimums and maximums are very important. And so first, the definition is for a relative minimum is the following thing. It's the point AB. So this is your relative minima, such that f of x comma y is bigger or equal to f of AB for all points x, y in some region around AB. So this is a relative minimum because it's not for all points, but it's for all points in some region. So we can think of, here's our function. So let's say this is our function. Its relative minimum is right over here, and that's at 0, 0. Now, this is also its maximum. This is also its exact minimum. So it is the minimum. It's not only a relative minimum, but it is the absolute minimum. But it's also the relative minimum because for points around 0, 1. So for all of these points, let's say, it's a minimum, right? All these points are bigger. F of them is bigger than f of 0, 0, which is equal to 0. So it's a relative minimum. And a relative maximum is the same exact thing, but now this sign is flipped. So it's the points. So for the max, you get f of xy is less than or equal to f of AB. So it's the top point. So if we, again, think about some function, and let's draw it like, let's say something like this. That won't work. Okay, let's say some function, and then here, let's say you have a bigger, oh, no, this. Okay, let's do it simply. So again, here's your maximum. It's your absolute maximum, but it's also a relative maximum because for all the points around it, for all these points around 0, 0, they get mapped to points that are lower than your 0.00. Any questions about what a relative minimum or a relative maximum is? Okay, so the same way that minimums in Calc 1 happen when your derivative is 0, so, and so do maximums, and also in just, you can have situations where your derivative is 0, but you don't get a minimum or a maximum. So for example, here is your maximum and your derivative over here is 0. So if this is f of x, at this point, f of c, f prime of c is equal to 0. And similarly with a minimum, all right, same exact thing, your derivative is 0. And of course, you can have a situation where the function looks something like this. So it's not a minimum or a maximum, but your derivative is still 0. So knowing that your derivative is 0 is not enough to know that it's a minimum or maximum. But if you do have a minimum or maximum, the derivative is 0. So in a similar situation, we have critical points in Calc 3. So AB is a critical point if the gradient of f of AB is equal to 0. So instead of saying that the derivative is 0, you have two directions and you want it to be flat in both directions. So you don't want the derivative of only the partial with respect to x, so only the partial with respect to y to be 0. You want both of them to be 0. And or if your derivatives don't exist, it might be a critical point, but we are not going to discuss those type of situations here. So what this means is, again, if you have your function, so let's do a simple function. This is f of xy is equal to x squared plus y squared. And of course, if you take your gradient of f at the point 0, 0, well, that is 2x. Let's just first do the gradient. So that is xy, 2x, 2y. And if you do the gradient of f at 0, 0, you get 0, 0. And so this point is, so this point over here at 0, 0 is a critical point. Any questions about this? Okay. So instead of, well, we did a small example, but let's go on to the second part, and then we can do an example for all of this. But in Calc 1, the first derivative tells us some information about our critical points, but the second derivative tells us the rest of the information, which is it a minimum or a maximum, right? So if, again, if you're in Calc 1, here's your X, here's your Y. Let's say that this is your F of X. So we know that if you're, in this case, your second derivative is going to be less than, or let's say equal to 0, right? And that tells you it's concave down and that you have a relative, that you have a maximum, right? And if your second derivative is bigger or equal to 0, it's just, then you know you have something that's concave up. And if it's equal to 0, you don't know anything. So in a similar way, our second derivatives also give us information, and it's in this form. So first, take D of AB to be the following thing. The second partial of f with respect to x. So the partial with respect to x, and then the partial of that with respect to x at AB times the second partial of f y at AB. Right, so far we're using the information contained in our second derivatives, right? Similarly to this situation, we put our second derivatives over here, minus fxy at AB squared. Okay, that's your D. Okay, any questions so far? So now, yeah. Yes. Yeah, that's an important formula which gives you tells you if something is a minimum or maximum. Yeah. I don't believe this formula has a name. I've never heard it. Okay, so 1. If D is bigger than 0, and the second partial of f with respect to x is also bigger than 0, then this implies you have a relative minimum. So what's a good way to remember this? Well, the first part is this, if this is bigger than 0, you're either a minimum or a maximum, okay? And we'll see in a second what happens if it's less than 0. But if it is bigger than 0, you're either a minimum or a maximum. Now, if this is bigger than 0, it's kind of like your second derivative being bigger than 0. Right? Kind of like that. Well, what do we know about this? That your function is concave up and that your point is a minimum, right? So that tells you that this is a minimum. Okay? Case number 2. If D is bigger than 0 and fxx is less than 0, and you can do this with fyy as well, but I would just recommend sticking to the script. So then you are a maximum. And again, first point is this is bigger than 0. So you're either a minimum or you're a maximum. Second point is if this is less than 0, you are concave down, so you are a maximum. Okay, case 3, D is less than 0, implies you're a saddle point. Okay, so like the horseshoe has a point which is not a minimum or a maximum, and if your D is less than 0, then you're a saddle point. And if D is 0, then there is nothing, you can't determine information about the minimum and the maximum from the second, from this D, from the information given in D. Any questions about this? Yep.
So does it necessarily mean it's absolute?
Oh, no, this is just relative. So this is all local information, partial derivatives at your points. You will not be able to get global information from information that's given near your points, right? This is all very local information. Does that make sense? Any other questions? Yeah. So we'll do some examples. Okay. Other questions? Okay, so let's do a example. So let's say your f of x, y is equal to 4 minus x cubed plus y cubed minus 3xy. And they ask us to find and classify all the critical points. And classify, which means is it minimums or maximums or saddle points. Okay. So first step, let's take the gradient, or let's take the partial of f with respect to x at x comma y, which is equal to negative 3x squared minus 3y, and set this equal to 0. Second step, partial of f with respect to y at xy. Well, that's going to be equal to 3y squared minus 3x. Now set that equal to 0. Okay, and then before we go on to the second partial derivatives, let's just find our critical points. So the first equation this should be a plus. And so this is not a thing. Okay, any questions so far? Okay, so the first equation, 3x squared minus 3y is equal to 0. Well, this implies that y is equal to x squared. Okay. Now, if y is equal to x squared, we can plug that into our second equation and get 3 times x squared squared minus 3x is equal to 0. And this tells us that 3x times x cubed minus 1 is equal to 0, which tells us either x is equal to 0 or x cubed minus 1 is equal to 0, which means that x is equal to 1. Any questions so far? So once we know that x is either 0 or 1, our critical points, well, we know what our y is. Our y is x squared. So we're going to have one point, which is 0, 0, and a second point, which is 0, which is 1, 1, 1. So these are our critical points. Okay, yeah. Okay, here, there. Any questions? Yes.
Actual points, like the x and the y.
So again, you're going to use these two equations over here. And so let's see what happens from the first equation. And this is kind of why you've been given in the past two homeworks the system of equations. It's important here and for Lagrangians. So you're given this system of equations. So solve the first one. So this is the first one. And you move the 3y to the other side, divide by 3, y is equal to x squared. Once you get the y is equal to x squared, you plug it into the second equation for this y. So you plug x squared in there, and that's right here. And then you just leave everything else the same. Now you have an equation only in terms of x, so you can solve for x. So here is what that equation becomes. which means x is either 0 or x is 1. So x is either 0 or x is equal to 1. And then if x is 0, well, you plug in 0 for your x, right? And you get y is equal to 0. And if x is 1, you plug in 1 for your x and y is equal to 1. So those are the 2 points that make this thing equal to 0. So you can try that. You can say, well, let's look at the point 0, 0, plug it in. 0 minus 0 is 0. Sure. Again, 0 minus 0 is 0. So that's the easy one. Okay, and then the other one is, any other questions? Okay, so now that we have our critical points, we can look at the second piece of information that we need, which is our d of xy, which is the partial of fxx, the partial with respect to y, minus the partial xy squared. Okay, so what is the partial of x twice? So going up here, we are asking for this partial with respect to x, so that is 6x. So we get here 6x. What is the partial with respect to y twice? So we go to the y, and that is 6y. So 6y. What is the partial with respect to xy? So we go either, well, let's go to the first one and say it's -3, right? Partial with respect to y, -3. Any questions? Okay, so now we set up this formula. D of xy is equal to 6x times 6y minus -3 squared, so -9, which is equal to 36xy minus 9. Any questions? Okay, so let's try it. Let's see what is d of 0, 0. So d of 0, 0, put in zeros here, is going to be equal to -9, which is less than 0. So let's go back to our classification. If it's less than 0, we're a saddle point, right? So this must be a saddle point. So 0, 0 is a saddle. Okay. Saddle point. Let's try this for 1, 1. So what is d of 1, 1? Well, that's going to be 36 minus 9, which is bigger than 0. So we know that 1, it's either a min, or 2, it's a max. So how do we determine which one it is? Well, let's look at the partial with respect to x twice. Plug in 1, we get a 6, right? So partial of x at 1, 1 is equal to 6. So it's positive. So it means it's concave up, which means we are a minimum. Any questions about this? Yeah.
What if partial with respect to x twice is 0?
Then you cannot figure out information. Any other questions? Okay. So let's do another problem. Okay. Let's say that f of xy is equal to 3x squared y plus y cubed minus 3x squared minus 3y squared plus 2. And again, we're asked to find and classify all the critical points. Okay? So first thing we want to do is what is the partial of f with respect to x? So that's going to be 6xy minus 6x. Okay. What is the partial of f with respect to y? That is 3x squared minus 6x. Okay. So these are our, y, okay, minus 6y minus 6y. Okay. Any questions about this? Yeah? Yeah. So I guess, minus plus 3y squared. Thanks. And any other questions? Okay. Let me just. Okay, so step number 2. Set these two things equal to 0. So let's just set it equal to 0. Okay, so what does the first thing tell us? It tells us 6xy is equal to 6x. Now, a very, very important thing to start remembering is when we divide, we have to keep in mind the 0 case. So of course we can divide the two x's, but only if x is not 0. So let's write either x is equal to 0, or we get 6y is equal to 6, which implies that y is equal to 1. Okay. So now what happens in both of these cases? So what happens if x is equal to 0? So let's go back and notice if x is equal to 0 and we do plug it in here, we get 0. So let's see what happens in the second case. So let's plug x is equal to 0 into this equation. So we get 0 minus 6y plus 3y squared. Let me put it, let's make a little table. Okay. So we get negative 6y plus 3y squared is equal to 0. Or in other words, 3y squared is equal to 6y. And again, we go to two different situations. First situation, y is equal to 0, right? And that will solve this problem. Second situation, if y is not equal to 0, we divide by y, and we get 3y is equal to 6, or y is equal to 2. Yeah. So let's write down the critical points that we have so far. We have the point x is equal to 0, y is equal to 0. That's this and that. We also have the point x is equal to 0, y is equal to 2. That's this, or let's do it this way, this and that. Yeah, any questions? So those are two critical points. What about other critical points? Let me just make sure. Good. So the other critical points are in the second case over here. So let's see what happens here. If y is equal to 1, y is equal to 1, we can plug that into our I don't know, maybe we can't plug it into that, I don't know. But we can definitely plug it into the second equation. So let's plug that into the second equation. And we get 3x squared minus 6 plus 3 is equal to 0, right? So this tells us that 3x squared is equal to 3. Or in other words, x squared is equal to 1. So x is equal to plus or minus 1. So now we have some more critical points. These critical points are x is plus 1. X is 1 and y is 1. Or x is negative 1 and y is 1, right? These points and these points over there. Does that make sense? Any questions? Yeah.
You can't plug it into the first one because you're just gonna get 6x. Right?
Yeah, the information came from there, so it's just, yeah. Any other question? So what did we end up doing? We took the partials, we set them equal to 0. We solved the first one, and we got two options. X is equal to 0, y is equal to 1. For x is equal to 0, we used the second equation, plugged in x is equal to 0, and got two critical points. For y is equal to 1, we plugged that into the second equation, and again, got 2 points. And those are also 2 critical points. So these are our critical points, and now we want to know what the minimum, maximum, or saddle points. So the next piece of information that we need is our d of xy. Rather than just writing down the formula again, I'm just going to take it. So 1 second. Okay, so it's the partial of this with respect to x. So that is going to be 6y minus 6 times the partial of this with respect to y. And that's going to be negative 6 plus 6y minus the partial of this with respect to y squared. So that is 6x squared. Any questions? Okay, let's see. Looks good. So what is the first one? D of 0, 0 is going to be, so this part is 0, and this is 0. So negative 6 times negative 6, which is equal to 36, which is bigger than 0. So if we have something that's bigger than 0, we check the first partial. So what's the partial xx of 0, 0? So that's this, and that's going to be negative 6, which is less than 0. And so if it's negative 6, we know that if it's negative, it's concave down. So we are at a maximum. Yeah. Okay, let's do another one. So let's do the 1, 1, 1. D of 1, 1. That's going to be 6 minus 6 times, okay, so that's 0 minus 6 squared. So this is negative. So this is a saddle point. So saddle point. So please take the next 4 minutes and do the other two. So do this one, 0, 2, and do this one, negative 1, 1. No, I don't make the homeworks or the answer key, so that's Matt, and he makes that decision. Okay, so let me finish this problem. So what is d of 0, 2? Well, that's going to be 12 minus 6 times -6 plus 12 minus 0. So this is positive. And so what is fxx at 0, 2? Well, that's going to be, let's say the partial of, so that's going to be 12 minus 6, which is also positive. So we are at a minimum. So we have a max, a min, a saddle point. What about the last one? So I'll just say the last one is a saddle point, and we can stop here. Have a nice day.